The National Electrical Code, or NEC, Section 210.20b addresses the sizing of conductors for branch circuits. Specifically, it outlines situations where conductors can be sized according to 210.20 bone, 210.20b2, or 210.20b3. 210.20 bone focuses on scenarios where a single transformer supplies a limited number of branch circuits. To elaborate, if a branch circuit is supplied by a single transformer having not more than 6 2-wire, 3-wire, or 4-wire branch circuits, supplying a total load of not more than 12 kV, and where the load consists of either firstly, not more than 8 2-wire branch circuits supplying receptacle outlets each not exceeding 1800 V continuous, or secondly, not more than 6 2-wire branch circuits supplying lighting loads each not exceeding 2400 V continuous, then the conductors of the branch circuits may be sized in accordance with 210.24. However, there's an exception: conductors sized in accordance with 210.24 are not permitted for branch circuits supplying outlets in dwelling unit kitchens, family rooms, dining rooms, breakfast rooms, or similar areas where appliances are likely to be used, or for branch circuits supplying fixed lighting units in commercial or industrial occupancies. This implies that while you might technically be able to use smaller gauge wire under these conditions in some parts of a circuit, certain areas and applications have stricter requirements. Now, while the code might permit a #12-2 wire for the home run of a 15 amp circuit, even if the rest of the circuit uses #14-2 wire, understanding the implications is crucial. This allowance comes with specific conditions. The branch circuit must be supplied by a single transformer with a limited number of branch circuits, specifically not more than 6 2-wire, 3-wire, or 4-wire circuits. The total load on that transformer must also be capped at 12 kV. Additionally, the load on the branch circuit needs to fall into one of two categories. The circuit can supply no more than 8 2-wire branch circuits, each feeding receptacle outlets with a maximum continuous load of 1800 V. Alternatively, it can supply no more than 6 2-wire branch circuits powering lighting loads, each with a maximum continuous load of 2400 V. It is important to note that this code rule is technically permitted under those specific conditions. Using different wire sizes on the same branch circuit is generally considered poor practice. The rationale behind this is simple: the smaller wire gauge will inherently have a higher electrical resistance compared to the larger gauge wire. This increased resistance can lead to a couple of significant problems. Firstly, it can cause voltage drop along the circuit. This means that the voltage at the end of the circuit, where the load is connected, will be lower than the voltage at the beginning of the circuit near the panel. This voltage drop can negatively impact the performance of electrical devices, causing them to operate inefficiently or even malfunction. Secondly, the higher resistance in the smaller wire can lead to overheating. As current flows through a conductor, it generates heat. The amount of heat generated is proportional to the resistance of the conductor. Since the smaller wire has a higher resistance, it will generate more heat than the larger wire when carrying the same amount of current. This excessive heat can damage the insulation of the wire, potentially leading to short circuits or even fires. Beyond the technical issues, using different wire sizes in the same branch circuit can also create confusion for electricians working on the circuit in the future. When troubleshooting or making modifications, it's essential to know the wire size used throughout the circuit. If different sizes are used, it can be difficult to determine the correct ampacity of the circuit and ensure that it is properly protected. To avoid these issues, it's generally recommended to use the same wire size throughout the entire branch circuit, even if the code technically allows for different sizes in certain situations. This approach ensures consistent performance, minimizes voltage drop, reduces the risk of overheating, and simplifies future maintenance and modifications. In practice, sticking to a uniform wire gauge for the entire branch circuit, despite the allowance for variations under specific NEC stipulations, provides a more robust and safer electrical installation. This minimizes potential voltage drops, mitigates overheating concerns, and streamlines future maintenance. Consider a scenario where a 15 amp circuit is wired with #12 American wire gauge or OG wire for the home run from the electrical panel to a junction box, and then transitions to #14 AWG wire for the remainder of the circuit feeding receptacles. While this might seem compliant under the previously discussed exceptions of NEC 210.20 bone, a #14 AWG wire, being smaller, possesses a higher resistance per unit length compared to the #12 AWG wire. When current flows through this mixed gauge circuit, the #14 AWG segment will experience a greater voltage drop than the #12 AWG segment for the same length. This voltage drop reduces the voltage available at the receptacles, potentially causing connected devices to operate inefficiently, especially those sensitive to voltage fluctuations. Furthermore, the higher resistance in the #14 AWG wire leads to increased heat generation. Although a 15 amp circuit breaker protects the entire circuit from overcurrent, the localized heating in the #14 AWG segment can still degrade the wire insulation over time, increasing the risk of a short circuit or ground fault. The difference in wire gauges also introduces practical challenges for future electrical work. An electrician encountering this circuit may incorrectly assume the entire circuit is wired with #14 AWG, potentially leading to the use of an inappropriate overcurrent protection device if modifications are made. For instance, if the electrician increases the load in the circuit, believing it to be entirely #14 AWG, they might not upgrade the wiring to a larger gauge, overloading the #14 AWG segment and creating a fire hazard. Therefore, maintaining a consistent wire gauge throughout the entire branch circuit, typically #12 AWG for a 20 amp circuit and #14 AWG for a 15 amp circuit in residential applications, ensures a uniform voltage distribution, minimizes the risk of localized heating, simplifies troubleshooting, and promotes safer electrical practices. While the NEC provides specific exceptions for using different wire sizes, these exceptions should be approached with caution and a thorough understanding of the potential consequences. A best practice is to prioritize consistency in wire gauge to enhance the overall reliability and safety of the electrical system. Consider a more detailed example of a residential lighting circuit. Imagine a scenario where the electrician runs #12 AWG wire from the circuit breaker in the panel to a centrally located junction box in the attic. From this junction box, they then branch out to several recessed lighting fixtures using #14 AWG wire. The total load in the circuit is designed to be under 15 amps, and the electrician believes they are complying with the NEC exception allowing for smaller gauge wire in certain situations. However, several potential issues can arise from this approach. Firstly, voltage drop becomes a significant concern. The #14 AWG wire has a higher resistance, leading to a voltage drop across each run to the recess lights. This can cause the lights to be dimmer than expected, especially those located further away from the junction box. Over time, this voltage drop can also shorten the lifespan of the LED bulbs used in the recess fixtures. Secondly, heat buildup is a real possibility. While the circuit breaker is rated for 15 amps, the #14 AWG wire is more susceptible to overheating than the #12 AWG wire. If the lighting load increases due to the addition of more fixtures or the use of higher wattage bulbs, the #14 AWG wire could potentially overheat, damaging the insulation and increasing the risk of a fire. Thirdly, future modifications become more complicated. If a future homeowner decides to add more lights to the circuit or replace the existing fixtures with more energy-intensive models, they may not be aware of the mixed wire gauges. This could lead to overloading the #14 AWG wire and creating a dangerous situation. Furthermore, troubleshooting becomes more difficult when mixed wire gauges are used. An electrician trying to diagnose a problem with the lighting circuit may need to trace the wiring back to the junction box in the attic to determine the wire gauge used in each run. This can be time-consuming and frustrating. To avoid these issues, it is generally recommended to use the same wire gauge throughout the entire lighting circuit. This ensures consistent voltage, minimizes heat buildup, simplifies future modifications, and makes troubleshooting easier. In most residential applications, Using #14 AWG wire for 15 amp lighting circuits is a safe and reliable choice. However, if the circuit is particularly long or the lighting load is expected to be high, using #12 AWG wire may be a better option. It's important to consult with a qualified electrician to determine the best wire gauge for your specific application. In commercial and industrial settings, the implications of using different wire sizes become even more critical due to the higher loads and more complex electrical systems involved. For example, consider a scenario in a manufacturing plant where a 20 amp circuit is used to power several small motors. The electrician runs #12 AWG wire from the panel to a distribution box located near the motors. From this distribution box, they then branch out to each motor using #14 AWG wire. This approach may seem cost-effective, but it can lead to several problems. Voltage drop can significantly impact motor performance. Motors are particularly sensitive to voltage fluctuations, and a voltage drop of even a few volts can reduce their efficiency, increase their operating temperature, and shorten their lifespan. The #14 AWG wire, with its higher resistance, will contribute to voltage drop, especially when the motors are starting up and drawing high inrush currents. Overheating can damage motor windings. Motors generate heat during operation, and the added heat from the #14 AWG wire can exacerbate this problem. If the wire overheats, it can damage the insulation on the motor windings, leading to a short circuit or ground fault. This can result in costly repairs and downtime. Compliance with safety regulations can be compromised. In commercial and industrial settings, electrical installations must comply with strict safety regulations. Using different wire sizes in the same circuit can make it difficult to meet these requirements, as it can be challenging to ensure that the circuit is properly protected against overcurrent and ground faults. Maintenance and troubleshooting become more complex. When multiple wire sizes are used, it becomes more difficult to trace circuits and identify problems. This can increase the time required for maintenance and repairs, leading to higher costs and lost productivity. To avoid these issues, it is essential to use the same wire size throughout the entire circuit in commercial and industrial applications. This ensures reliable motor operation, minimizes the risk of overheating, simplifies maintenance and troubleshooting, and helps to ensure compliance with safety regulations. In most cases, using #12 AWG wire for 20 amp motor circuits is a safe and reliable choice. However, if the circuit is particularly long or the motor load is expected to be high, using #10 AWG wire may be a better option. It is always best to consult with a qualified electrician to determine the best wire gauge for your specific application. The National Electrical Code provides specific guidelines for conductor sizing, but it is important to understand the underlying principles and apply them judiciously. While the code may allow for certain exceptions, it is always best to err on the side of safety and reliability. Using consistent wire sizes, properly sizing conductors for the expected load, and following all applicable safety regulations are essential for creating a safe and efficient electrical system. Remember that electrical work can be dangerous, and it is always best to consult with a qualified electrician if you have any questions or concerns. They can assess your specific needs and provide guidance on the best way to design and install your electrical system.